Saxon Advanced Mathematics, Lesson 55. The topic is fancy permutations. We've done permutations. We're going to review basic permutations, and then we're going to add a few special tricks. All right, let's say that we have 3 members of a royal family who want to sit in a row at a banquet table. Okay? We have a prince, a king, and a queen. So, if they're sitting at a rectangular table, then there are 3 people who could sit in the first chair, 2 choices to sit in the second chair. Obviously, we can't replace them because who can replace a royal family? And then there's 1 person left to sit in the last chair. So, we multiply these together, right? And so we find out there are 6 ways that our royals can sit at a rectangular table. But now what we want to talk about is what are called circular permutations. How can we do this same type of calculation? I'm drawing a little box here that represents the chair. This one's kind of small because it's bumping up on the other ones. A circular permutation is different because it doesn't matter who's sitting where. It's just a question of who's sitting by each person. Does that make sense? We could spin the table and have them sit in different seats, but it would still be the same arrangement. So when we are doing a circular permutation, this is the rule. We have to have someone sit down first. Somebody just has to sit down. Doesn't matter which chair, but we have to pick one seat and just say one. Somebody sits there. That's it. Okay? Now when we go to the next seat, well, there's 2 choices, and then there's 1 more choice. So when we do a circular permutation, we remember that rule, and there are far fewer ways. This is what we call a linear permutation. And obviously the fancy name just comes from, are we arranging in a line or in a circle? So the thing about a circular permutation is the first box always gets a 1, not a 3. Because granted, anybody could sit there, but somebody just has to sit down. That's how I remember it. All right? So in these problems, we're often asked to calculate both. Example 55.1. How many ways can 6 different items be arranged in a line? And how many ways can the 6 items be arranged in a circle? Okay, so it's the same thing only with 6 instead of 3. So for a linear permutation, let's go ahead and draw out the boxes. We could use that formula that we learned at some point, but I think the formula confuses the issues. Let's just do it the way we know how. So, for the linear permutation, they're physical items, so they're obviously not replaceable. That's the basic way. We've been doing it all along. And that is equal to 6 factorial. And you can use a calculator on that and find out it's 720 ways. Now, let's do the circular permutation. Now, even though they're sitting in a circle, we often write out the boxes the same, which is a little confusing, but remember, this is just to keep track of our numbers. And we remember this rule. The first person must sit down, or in this example, the first item just has to be given a place. So in the first choice, it's only 1. And then we go from there. Then there's 5, there's 4, there's 3, there's 2, there's 1. So that equals, notice that we can substitute, we can explain this as saying that's 5 factorial. So again, with your calculator, you can find it's 120 ways. You could also find this by taking this number and dividing it by this number rather, and divide it by 6, right? Because that's the number that isn't in this one. Okay, so notice, it's kind of interesting, right? When you arrange things in a circle, there are far fewer ways to arrange them than if you're arranging things in a line. All right? Okay, and then there's one more example of these. Circular permutations, which is what our first topic is today. We have two topics. 55.2. When the chips were down, Ed found that there were 5 chips and each one was a different color. How many ways could Ed place them in a row or in a circle? The whole thing about the chips being down and all of that, that's just John trying to confuse us. We still have the same pattern. It's 5 items that are physical, so we know we're not replacing them. And when we put them in a line, there are 5 different ways to do it. And I don't even need my calculator to know that's the same number. Now let's try it in a circle. And again, we're drawing a box, but we're talking about how many choices there are. And again, the trick to circular permutations is you just got to put the first one down. 1. 4, 3, 2, 1. That's 4 factorial. We could also divide that by 5, couldn't we? And that becomes 24. All right, these are all the right answers. Okay, so this is the trick. The first item, you just have to put it down in a circular permutation, and it only counts as 1. If you can remember that, but you're not exactly sure how that's logical, that's okay. Just be happy to understand it and remember it, all right? I'm going to confuse you now because we're going to do another fancy permutation, and this is slightly different. This is called distinguishable permutations. Let me explain what this works. Let's say that we have the word cat, and we're trying to find out how many linear permutations of this we can find. Well, we know it would be 3. Oh, no, yes. They're not physical, so we can replace. Is that right? I just want to make sure. Yeah. No, we're going to say that they're no replacement. With letters, it could be either way, right? Because we could have Scrabble tiles. But we know it's 3, 2, 1. That's 6 different ways, right? Without replacement. But what if we're doing the word moo? Well, we'd still say 3, 2, 1. That's 6 ways. But let's call it O1 and O2. So we could do M, O1, O2 as one of the ways. And then we could switch the O's around, right? And we can continue doing that for all the different permutations that we are deriving, right? So there's the 6 different ways, but you see that pairs of these are really exactly the same. It's only with our silly little subscript that you can tell the difference. So what we're saying is that sometimes when some of the items are the same, you kind of have to factor that in and show that it really doesn't make, there aren't as many different permutations because they look exactly the same, because some of the elements are the same. So we have a nifty little formula. So in this example, this is the little formula we're going to use. We're going to take the number and we're going to divide it by the ones that are the same. So in this example, we would say it's 3 factorial over 2 factorial, because we have 2 of one kind, right? And so this would be 3 times 2 times 1 over 2 times 1. That means we'd have 3 ways. And that's exactly what we found, that there's only 3 distinguishable ways to do those, okay? So this is the formula we're going to use. And what's interesting is that in this set of items that we were arranging, we had one type of item that repeated, but in more complicated problems, we might have more than that. So I'm going to copy this onto the next page and show you how we deal with a slightly more complicated situation. All right. Example 55.3. Jojo, oh my gosh, it's Jojo Hepler. She's in our problem. Jojo has 10 marbles. 3 are red. Ooh. 3 are red. 3 are blue. 4 are green. How many distinguishable permutations of the 10 marbles can be formed? All right, so we can see, we've got lots of repeats here, right? So this is how we do it. The number factorial of items. So it's 10. And in this case, we have 3 different items that repeat. So we're going to label each one of those repetitive sets by a different number. And we're going to show that this can be expanded so that you divide by however many letters you need for all of those duplicated sets. And so then the way we do this is it's 3 factorial, because we have 3 items in one, and then we have 3 items in the next, and then we have 4 in the next. Okay, so these numbers are the numbers that I divide by. Make sense? Ish. Then we can do the math on this. This is kind of fun to do by hand. It's really windy outside. 3 times 2. I'm going to leave the ones out. Times 3 times 2 times 4 times 3 times 2. Right? That's 3 factorial without the 1. That's 3 factorial without the 1. That's 4 factorial without the 1. That's 10 factorial. All right, so what we do now is just play around and see what can we eliminate. So 3 and 3 is 9. 4 and 2 is 8. 6 and 2, or 3 and 2 is 6. And so our answer is let's see, this is, I'm not sure I canceled right. I think I got a little crazy. Let's do it again. 9 is 3 times 3. 8 is 2 times 4. 6 is 3 times 2. And then 2 goes with 2. Oh, there's the 7. That's what I was missing. Okay. This much is 20. This is 21. So we had 20 times 21 times 10, right? 20 times 21 times 10. So that is 200 times 21, right? I put those two together. And so what we find is that there are only 4,200 ways that these marbles can be arranged so that there are actually different patterns, right? If we find the total number of permutations for 10 items, it's really big. Let me find it. John has it in here somewhere. It's 3,628,800. 3,628,000, is that what I said? 800? Let me double check. Yes. Okay, so if we just did a calculation of the number of total permutations where we didn't take into account the fact that some of the marbles were the same colors and that the arrangements were going to look exactly the same, we'd have almost 4 million. This way we only have 4,000. Interesting, right? It makes a big difference. All right, 55.4. How many distinguishable permutations can be formed from the letters in the word nonsense? Nonsense. 1, 2, 3, 4, 5, 6, 7, 8. So we know that 8 factorial is how we could find the total number of permutations if we weren't worried about the fact that we have repetition. Now we have to divide by the factorial for any groups of numbers, right? It might be more than one. Well, let's see. Oh, we've got 3 n's. So there's the first one. Just 1 O, 2 s's, and 2 e's. Make sense? We're using that formula and we're dividing by the number of items that repeat. It's kind of hard to put that to describe what these A, B, and C represent, but you can see it in the calculation. My words are failing to describe it succinctly. 8 factorial, 322, that's correct. And the number, if you use your calculator or do it by hand, I think it's more fun to do it by hand, it's 1,680. Okay, and then the last problem for lesson 55 is this. How many distinguishable 7-digit numbers can be formed from the digits in, here comes the number, 2, 7, 2, 2, 4, 2, 4. Okay, so we're trying to find 7-digit numbers. Notice that in all of these cases, we were using all of these. So it's a pretty straightforward original calculation. So we know the top is going to be 7 factorial because it's 7 items arranged in sets of 7. All right. Then we have to divide by any duplication. Okay, 1, 2, 3, 4 2s. So that's 4 factorial. There's just the 1 7, and then there's 2 4s. Okay, so we're dividing by the number of repetitions of any particular element. And then this will turn out to 105 ways. Have I been boxing my answers? I don't think I have. Oh, I haven't. Yikes, you guys. Not okay. Okay? Yay. That's the end of lesson 55. 2 different tricks. Distinguishable permutations, we have to divide by the factorial of the number of any elements that repeat. And circles, we have to start with a 1 because somebody just has to sit down. You just have to put the first thing down when you're working with a circular arrangement, and then you go on from there. So the first item is always 1. All right, that is the end of lesson 55. I will see you very soon for lesson 56. Goodbye.